Good morning. I'm Julia Kubanek. I'm a professor of biological sciences and chemistry and biochemistry. And my labs here at Georgia Tech are across the quad in the Ford ES&T building, where we are co-located with other environmental scientists and engineers. And my students and I also perform field research at various sites around the world. Our group's research interests lie at the intersection of chemistry and biology, where we try to understand how living organisms communicate with each other and interpret information from their environment using chemical signals. So an example of a long-standing project that we've held in our lab, actually since I joined Georgia Tech in 2001, has been to understand the ecological impacts of the toxins that are produced by harmful algae that include red tides, and the interactions of these toxins with other members of marine communities. So there are microscopic predators and competitors in the marine environment that release chemicals into the water that affect the toxicity of these marine algae and therefore affect downstream human health issues and also contaminate shellfish, so they affect the fisheries industry. And so this increase in toxicity of harmful algae that's caused by chemical signaling between organisms can change the environmental impact of harmful algae by making these harmful algae up to 20 times more toxic with dramatic consequences. But our major sustainability-related project in the lab right now is a new project that we started last year in collaboration with Sandia National Labs and also 3 other universities in the US. And there we're focusing on algal biofuels and trying to make them more productive, so to increase their biomass, more high quality, that's to increase their lipid content, and therefore increase their long-term economic feasibility. Algal biofuels are not currently commercially feasible. There's plenty of doubt, in fact, in industry and in government that they can be made feasible. To be sustainable and profitable, what we have to do with microscopic algae is grow them up, harvest them, and turn their biomass into fuels, and the lipids into fuels. Now, technically or theoretically, this should be a carbon neutral process because the carbon that's released when we burn the fuels from algae would be the same carbon that's fixed when we grow the algae in the first place. Now, to make this process work, the algal cultivation has to be done at large scale. Typically, this is done in ponds that are called raceway ponds in the outdoors. We have 6 of these ponds at Georgia Tech off of North Avenue at the TEP site. And the algae in cultivation there are circulated in order to keep the system oxygenated and to let the sun do its work. But there's something that biofuel researchers don't often talk about, which is because of the outdoor nature of this venture, up to 90% of the biomass can be lost really early in the cultivation process, due, strangely enough, from critters that fall from the sky. And I mean that literally. So there are microscopic animals called rotifers that can exist as eggs that can last for months or years in the environment, and it's impossible to keep them out of algal ponds. And so these eggs then hatch, and little rotifers swim around in your pond, and they eat all your algae. And then there's other algae that can contaminate the pond, and those other algae act as competitors with the biofuel-producing species that you want to grow. And there are pathogens and parasites that also can grow. And so these are not sterile systems, and to become commercially feasible, they cannot be made into sterile systems. We have to deal with the wilderness that exists in an algal pond. All of these processes that occur in these ponds that include predation, competition, and parasitism. These are all ecological processes that occur in every other single ecosystem on Earth. And over the billions of years that organisms have evolved, many microscopic organisms have developed traits that allow them to be protected against some of these enemies. So the goal of our project at Georgia Tech is to exploit natural products to protect biofuel algae from predators and pathogens that infect the ponds. So we already know that some of the bacteria that naturally co-occur with the algae in these ponds produce chemical compounds that can be helpful to protecting the algae themselves. And we know that these compounds are there because we can generate filtrates of the bacteria and show that they protect the algae from rotifers and from parasites. But we haven't yet identified what those natural products are. And the idea, if we could leverage natural products to protect biofuel ponds is that this would not be as harsh as the current uses of bleach or copper sulfate or other chemicals that are sometimes deployed to try to prevent the infection of ponds by these other organisms, but those other chemical treatments end up killing the algal, the desired algae as well. So we're using a chemical profiling technique called metabolomics to identify the natural products that are associated with the members of the microbiome in the ponds that are the most protective. And then we will directly test those natural products in the lab and in pond experiments. So in the larger project with Sandia National Lab, our natural product solutions will be combined with GMO bacteria that are evolved to attack parasites that infect the ponds, with additional lab-based experiments, experimental evolution approaches that will essentially selectively breed the best algae that have high growth and high lipid content, and also with real-time field-deployed gas chromatography methods to diagnose ill ponds or sick ponds and therefore intervene earlier in the growth process. So overall, we're planning to use, or we're starting to use, ecological and evolutionary principles to improve algal biofuel production and therefore make this possibly economically feasible in the future. Thank you very much.